up. Thank you for coming. This talk is about EOF. We had a very nice introduction. Thanks, Alex, in the previous presentation. So hopefully you know by now this is a series of proposals that aims at redesigning and improving EVM in various ways. And I will be talking about one part of it, one EIP 5450 stack validation. Stack validation is, in general, one part of a bigger code validation procedure that happens before code is being deployed on chain. And one of the leading principles and main goals of it is to get rid of repeated checks during executing the same code. And instead, if we can do the check once before code is being deployed, then we do that and then assume it is satisfied during execution, and then basically we can omit the same checks at runtime. For stack validation in particular, this means ensuring stack correctness of every instruction in the code, and in EVM, as we don't have types of the values on stack, this simply means making sure that none of the instructions overflow or underflow the stack. And given that we check this once at validation, then we can omit these checks from the interpreter loop. And one important consideration to keep in mind when designing stack validation is keeping its complexity linear in the size of the code. This is important because we cannot afford having some worst case bytecodes exploding validation time and enabling DOS attacks with that. A very high-level overview of how stack validation would work. We go through control flow of the graph, control flow graph of the code, examine every instruction and see how many values it pushes or pops from the stack, and keep track of what is the current stack height. If it ever goes below 0, we detect underflow. If it ever goes above stack height limit, we detect overflow and reject this entire code as invalid and do not allow for it to be deployed. This sounds pretty simple and high level, and you might wonder at this point, how is this even possible to achieve without executing the code, because we are used to thinking about underflows and overflows as depending on the runtime value of the stack height and depending on whatever runtime conditions on call data or storage or whatever. I will show you that, in fact, this is possible given that we impose one extra restriction on what is allowed in the code. So let's zoom in and explore how this would work. This was our initial approach to this problem. And let's discuss underflows first. Overflows are handled quite differently. I will mention this later. So every section is validated independently, one section at a time. We traverse the control flow graph of the code in a breadth-first search or depth-first search manner, meaning we follow every jump. If it's a conditional jump, we follow both branches of the jump. We keep track of what is the current stack height for every instruction and record it. If it goes below 0, we detect underflow and reject this code as invalid. And one extra restriction that makes it all possible is the rule. If we ever encounter an instruction that during our traversal that was already visited before, it means that this instruction may be reached via multiple possible code paths during execution. And in this case, we require that the stack height at this instruction is equal for all possible code paths leading to it. So this is something new comparing to current EVM. So this makes some of the patterns that were possible in current EVM invalid now in EOF. As a practical example, for if then else statement, you would be required to have equal stack height at the end of the then and else branches, for example. Or for loops, for example, the loop body is not allowed to grow or shrink stack. These are pretty reasonable restrictions to have. Other VMs also have similar rules like JVM and WebAssembly. And thanks to this rule, we just, when we get to the branch that we have already seen, we just check this condition and do not revalidate the same branch. So in the end, every branch is validated exactly once. Every instruction is visited exactly once. So complexity is linear for this algorithm, which is what we desired. So this is great. And one extra rule that we have, if after the traversal is finished, some of the instructions are not visited, it means they are never going to be reached in execution, and we do not allow this. We do not allow unreachable code to be deployed and reject an entire bytecode as invalid. I will show an example now how this would work. So here's the simple code. We'll need an array of stack heights for every instruction, and work list here is a queue-like data structure that keeps track of which branches we have yet to validate. So we start with the first branch at offset 0. Push instruction would add one value on the stack, then call data load doesn't change the stack height. Then this conditional jump instruction has two possible successors. At offsets 10 and 5, we add them both into the work list, and at this point we also have to record the stack height at both of the targets. Stack height is 0 after rjump I, so we record that at both offsets, and continue then with the next branch from the work list. We go to offset 0 there's a push and another push. Then as store checks whether it has enough items not to underflow. 2 is exactly enough for S store, so no underflow happens. We are good here, and we continue. This stop then validates, concludes validation of this branch, and we have still one branch left to examine at offset 5. We go there's another push, and then another jump into the target that we have already visited before. At this point, we have to check whether current stack height is equal to what we have recorded for this target before. It was 1 previously, and stack height is also 1 for this after this rjump, so 1 equals 1. And so this is valid. We do not revisit this branch anymore, and then we do not have anything else in the work list, and this concludes the validation. This code is valid in the end. Compare this to this invalid code. It is very similar, but with one push omitted, so it goes through very similar steps and ends up at this rjump instruction. And at this point, stack height is 0, but we have seen stack height 1 at the target before, and so they are not equal, and this means code is invalid and rejected. So this exact restriction that makes it all possible turned out to be problematic in some important cases. So this code, like on the slide, can be commonly generated by Solidity. For example, when you have a series of require statements in Solidity, every require is a check and revert in case it's not satisfied, and then Solidity optimizer at some point extracts these reverts into a common code block, and then each require becomes this check and a jump into this common code. So the problem here, these requires and these checks and jumps can be located at arbitrary points in the function code and at arbitrary stack heights, and this goes specifically against our rule that stack height must be equal at every jump into common code. Compilers could deal with it with some workarounds. For example, they could insert some extra pop instructions before some jumps to equalize the stack and make it equal for every jump into a common code. But this would mean increased code size and increased gas consumed, so this entire optimization might not be worth it in the end. Or another workaround could be to take this revert and make a separate code section out of it and call it from here. This would also work, but this also has an overhead of declaring this extra code section in the EOF header, putting its metadata into the type section. So in the end, code size also is increased, and we might have some regressions comparing to current EVM. This is something we really would like to avoid. And this is just one common example. It's not the only one. In general, compilers are very much in favor of being able to jump into some common helper code blocks from arbitrary stack heights. So we found a solution to this, and this is current spec of 5450 and final one. So we have to modify our algorithm somewhat in some important ways. We start with allowing multiple possible stack heights for every instruction. Instead of recording just one stack height value, we record the range of stack heights to minimum and maximum for every instruction. We change the way we traverse the code. Instead of depth first search or breadth first search traversal, we just do a sequential pass through the code front to back. Just a simple loop. We do not follow jumps when we see them. Instead, we handle jumps differently depending whether it's a forward jump or backwards jump. So depending on its relative offset, and this is known at validation time because EOF has static jumps instead of dynamic jumps. So we look at this offset. If it's a forward jump, we always allow it, and we just record the stack height at the target instruction. If we have already visited this, or we have already seen this target instruction before, we expand the stack height range of the target. And this specifically fixes our problematic case. We always allow these jumps into a common code, and thanks to sequential traversal of the code, by the time we reach the validation of this common helper, we have already seen all forward jumps into it, so we have seen already all stack heights at all of the jumps into this common code, and then we validate it using this stack height range that we have observed. So this fixes the problem, and as for backward jumps, we still keep the exactly same restriction as before. We require equal stack height at the jump instruction and at the target of a jump. This means that loops that grow or shrink stack are still not allowed. This is pretty reasonable restriction to keep. No compilers generate such loops anyway, and so they are fine with it. If this backwards jump is in fact a jump into a helper, not a loop, this code always can be reordered in a way that jumps into a helper is a forward jump. So this is kind of an implicit requirement to put on the code ordering for compilers too. And this is always can be done, and so compilers are fine with this. If we see a regular instruction which is not a jump, we just modify both ends of the stack height range, both minimum and maximum. Stack underflow is checked obviously using minimum end of the range. And one extra restriction or one change in how we define unreachable code. This is very much related to backwards jump rule that I have already mentioned just now. So we also expand a bit the definition of what is unreachable code. If some code is reachable only via a backwards jump, we also consider it unreachable now. This is needed to make this sequential traversal possible. And this is also always achievable by compilers. They need to do some kind of topological sort ordering of the basic blocks in the code, and it always can be done. So this restriction is fine. Some other VMs also have similar rule. And also because we have this simple loop over all instructions, every instruction is visited exactly once, so we are still fine complexity-wise. Complexity is still linear. I'll show an example how this would work now. So we'll need an array of two arrays of minimum and maximum stack height, or array of pairs. Note that we do not need a work list here because it's just a simple loop over instructions. So we start with the first one. Push is a simple instruction that modifies both minimum and maximum. So 0 to 0 becomes 1 to 1. Call data load doesn't change it. Then this conditional jump, it is a forward jump, so it is a load, and we have just to record the stack height at the target. It is 0 after our jump I, so we record 0 to 0 at offset x. Then we continue with the next instruction. This is another push and call data load, and then another conditional jump that targets the same offset that we have already seen before. At this point, stack height is 1 after our jump I, and we have to, at this point, expand the stack height range that we have seen at the target before. So 0, 0 becomes 0, 1. Then we have a stop with an extra value on the stack. This is allowed and valid. And then we get to this branch. This is interesting branch because it has multiple possible stack heights. It can be either 0 or 1 here. Then push would modify both minimum and maximum, so it shifts the stack height range. 0, 1 becomes 1, 2, and another push. And revert checks for possible underflow using minimum, and 2 is exactly what revert needs, so no underflow happens. This code is valid in the end. This concludes the validation. Note that this code is very similar to the problematic case that I showed a couple of slides before. This is like a common helper that reverts and a couple of jumps from different stack heights into it. So given this algorithm concludes successfully, we are guaranteed that no underflows happen at runtime ever at all. And we can completely omit them from the interpreter loop. This is not the case with overflow checks. We cannot remove them completely, but we can minimize how often we do them and not do them for every instruction as current EVM does. So to make this work, we start with what previous underflows validation algorithm gave us. We recorded stack height at every instruction in this algorithm, and we can just find maximum of these stack heights, and this value is going to mean maximum stack height value of this function's frame. If this value is above stack height limit, it means execution of this function may overflow, and we reject it immediately at validation. We do not allow it to be deployed. If it is within the limit, we record this maximum stack height value in this function's metadata in the EOF header. And then this value is used for validating the calls into this section, and also at execution time when we execute call F or jump F into this function. So in the end, we only have to do runtime overflow checks at two locations in the code. For when we execute call F or jump F, we get the current runtime stack height. We add it up with maximum stack height of the callee. If this sum is above the stack height limit, we do not allow call F or jump F. We exceptionally abort at call F or jump F. Otherwise, execution could overflow execution of this EOF function. So this is how overflows are handled. And one final thing that I wanted to mention is non-returning functions and jump F. These are defined in their own EAP, but they are closely related to stack validation and partially motivated by stack validation, I would say. So non-returning functions are those that do not return control back to a caller. They do not execute retf instruction. Or you could think of them as functions that end entire contract execution with instructions like stop, return, revert, etc. How is this relevant to stack validation? So when we validate a call to such a non-returning function, if there's some code immediately following this call, this code is never going to be executed at runtime because this call is non-returning. This means that we do not need and we should not validate this code following the call to non-returning. Instead, we should consider it unreachable and reject it as we do with other unreachable code. So to make this work, stack validation has to detect calls to non-returning functions somehow. For that, we have a special flag in the EOF header in the function's metadata. So when stack validation detects a call, when it sees a call, it checks this flag, whether it's returning or non-returning. If it's a call to non-returning function, it considers this call to be a terminated instruction. And then, in the end, then if there's some code immediately following it, it may be unreachable unless there was some previously seen forward jump into it. So this is how it works. What's important here is that calls to returning and non-returning functions are validated very differently. So for calls to returning functions, you have to take into account how many values were returned, put them on stack, and continue validation, and calls to non-returning are just terminating instructions. Given this difference, I would say a separate instruction for calls to non-returning is already justified. So this is exactly what jump F instruction is. If you need to do a call to non-returning function, you use jump F for that. Call F to non-returning is not allowed, in fact. Jump F also has a different use case. It can be used with returning functions, but this does not fit this presentation. But you can read more details in the EIP or some discussion at this another link. And this is all that I wanted to say about this. Thank you. Yes.
Thanks a lot. That was a very interesting presentation. So let's start with the questions. The most popular one is, could the stack validation allow translation to a register-based instruction set internally, reducing dispatch overhead in the interpreter loop?
I think definitely it can. Any translation is easier in EOF, given that we do not have dynamic jumps. That's the main reason that we can do JITing, we can compile to whatever backend. There are various ideas about what EOF can be compiled to. Interesting topic, yeah.
Okay, the next question is, since stack size can vary with recursion, which is only known at runtime, how can this method ensure stack overflows is detected statically?
Good question. So it is, we still require runtime checks for overflow. We just don't do them every time at every instruction. So the recursive calls will still do the overflow check when they do a call-off or jump-off instruction, and in case this call may overflow, this call is not going to be succeeded. So overflow checks are not checked completely statically. That's the answer.
Great. So the next question, I think in the beginning, you mentioned that some compiler optimizations won't be worth it. So I guess which compilers optimizations won't be worth it?
Yeah, so I referred to this one specific case that was pretty common for our initial idea of stack validation. The optimization that I meant was deduplication that Solidity compiler does when it sees a similar code at multiple points in the bytecode. It gets them and extracts them into a common helper. But like with the first algorithm, there was some overhead, and in the end, this might not be worth it. And because code size in the end may increase, and gas also increased.
Why does this needs to be part of EOF instead of just relying on the compiler to handle stack access efficiently?
Interesting. Well, I would say there is a value, definitely some value in ensuring stack correctness of the bytecode itself, because it can, bytecode itself then can be audited or can be formally verified or can be statically analyzed. So stack validation and validation in general simplifies these tasks and immensely, I would say. So that's the answer, I think. So if it wouldn't be enforced on the protocol level, then at high level, the same, only the high level language code would be available to use these benefits, I think so.
Makes sense. So the next one is if the code passes stack range validation, is it possible that there is a code path that under overflows the stack?
There is a possibility of overflows, but not underflows. That's the answer, yeah. Underflows are completely eliminated thanks to static validation at deployment time, and overflows still can happen, but we do not need to check them at every instruction, as I said.
The next question is if stack validation makes ZK cross-compilation or ZK trace arithmetization easier or harder?
It definitely makes it easier if, in case this ZK compilation targets EOF, only EOF, and does not try to support legacy too. In case it is ZK system that tries to support both legacy execution and EOF execution, then it has to basically support two different systems. That is a big pain, I guess. So it's generally much better idea to support EOF for them, and then thanks to code validation and thanks to deleting code observability, ZK compilation becomes much easier. That's at least the theory, and yeah, we'll see how this works out.
Okay, and I guess last question. Will gas fee reduce after this optimization, and if so, how much?
So there's no exact plans to reduce gas, but we definitely will see some improvements in execution time, and this might lead to some optimizations in the future. There will be gas savings thanks to better stack management. This is like not specifically related to validation, but rather to a better instructions to handle values on stack. We have now swap and append and exchange, and all this simplifies life for compilers, and in the end reduces gas consumed for entire execution.
Great.
How much can I say?
Let's thank